Okay, in this section we're going to be talking about the expedited field survey and sampling techniques that we've been developing for PCBs, which is polychlorinated biphenyls in the environment. The objective of this part of the study was to develop a fast on-site method for the determination of PCB congeners and dioxins. I'm going to talk a little bit about what congeners are in a few minutes here, in sediment samples and soil samples using this portable instrument that we've been helping to develop, this gas chromatograph mass spectrometer, or GCMS. A little bit of an introduction to PCBs just to make you familiar with the difference in terminologies we're going to be using between PCB congeners, which are specific compounds, and aerochlores, which is a mixture of PCBs. And so most importantly, what is a PCB? This biphenyl is these two aromatic rings that are stuck together by this carbon-carbon bond here, and we're going to have any number of chlorine atoms sticking out any position here. And you can imagine a scenario, if you only had one chlorine atom, it can stick out this 2 position, or maybe this 3 position, or 4, or maybe the 5' or 4'. If you had 2 chlorine atoms, they can be in almost any number of combinations. And these particular polychlorinated biphenyls can be substituted by up to 8 or 10 different chlorine atoms. They have different levels of toxicity depending on the amount of chlorination, and some of them are more harmful than others, more toxic than others, and 12 of these particular compounds, or specific congeners, specific orientations of chlorine atoms in these positions, are on the World Health Organization list of concerned chemicals. They have a list of a variety of harmful effects causing cancer, chloracne, otitis media, things like this. And one of the most problematic areas here is that they can bioaccumulate. In other words, they're very fat soluble, so any particular animal in the food chain that ingests these polychlorinated biphenyls, they can become concentrated in any lipid tissues. So that basically the concentration will build up, and then the higher up the food chain you go, the more concentrated they become. The main uses of these, why we even use them, were from the late 20s to the late 1970s. They were used as a variety of industrial applications like lubricants, coolants. Electrical insulators was the primary one. They were excellent electrical insulators. They were banned in 1979, though, because after a variety of spills into the environment, it became aware that they were very harmful. So let's look at the difference between congeners and aerochlores. A congener is a specific conformational isomer of a polychlorinated biphenyl, so maybe 2 chlorine atoms in specific positions. An aerochlore is a mixture, is a commercial name for a mixture of any number of congeners. One example in the port site that we've been studying is known to contain very low levels of a particular aerochlore called 1260. And the name here isn't just made up, it really has some chemical origin, and that is the first 2 digits come from the number of C atoms, the number of carbon atoms. This is the biphenyl, so most of the aerochlores are going to have a 12 here. And then the second 2 digits, the 60, is the percent of chlorine by mass in the final product, the commercialized product. In this particular case, if 60% by mass is chlorine, then it's going to be a 1260. So there's a variety of different aerochlores that have been used over the years, and 1260 is a particular one in the site that we're looking for. A little bit of background as to other techniques that are available for measuring PCBs in the environment. Traditional methods, first you have to take the PCBs out of the soil and then try and analyze them. And the most common way to get the PCBs out of the soil is to use a technique called Soxhlet extraction, where you basically boil organic solvents through the soil and to help solubilize the PCBs. Instead of boiling it through, you can use pressurized fluid extraction, which is basically forcing a hot organic solvent through the soil. You can put the soil in a microwave with the organic solvent. You can use ultrasonic extraction, like they would in a jeweler's. Supercritical fluid, so the same technique that they use to decaffeinate coffee. So a variety of these are recommended methods for removing PCBs from soil. Most of these are time-consuming, especially Soxhlet extraction. You have to reflux it for multiple, like 24 hours. There can be complicated apparatus, maybe lots of condensing or high pressures, things like this. Large power consumption and lots of organic solvents, and none of these are really amenable to portable on-site applications. So we've been using a commercial method called solid phase microextraction, and we're going to describe this in a few moments as a way of helping to remove the PCBs from the soil. There are already a variety of traditional methods, benchtop instruments, so you can go to a laboratory and find these big instruments sitting on top of a bench, and they do an excellent job of identifying the extracted PCBs, the PCBs in these organic solvents. And these commercial techniques are gas chromatography mass spectrometry, gas chromatography electron capture detection, or gas chromatography electrolytic conductivity detection. Most of these are quite time-consuming as well, because it's a lot of work to separate all these different congeners that are in these complicated aerochlor mixtures, and so it takes a long time to separate them all. And of course, these portable benchtop instruments are not easily transferable to the environment, to the soils where we want to make the measurements. So we've been developing a method for this commercial instrument. It's been available for a few years. It's made by Tor-Ion. It's called the Guard Ion 8 is the particular model we have. And it's a GC mass spec, and so it can separate a complex mixture of PCBs or any other volatile, and then it has a detector that can measure the mass or the fragmentation pattern of any one of those PCBs at any given time. It has a battery for operation in the field. It has its own helium helium cylinder for helping to move the PCBs through the instrument, and it comes with its own particular SPME sampling device, this custodian they call it. And on the end of this device here is this fiber that I'll talk about in a few minutes. One of the aspects we've had to develop to kind of go along with this instrument is a way of extracting these PCBs from the soil in the field on site. And to do that, we've kind of come up with this portable balance, just a battery-powered balance for measuring the mass of the soil, and then just a heating plate that's surrounded by this Pyrex just insulator, really, to stop the wind cooling the sample too much. There's an aluminum block inside to help keep the temperature constant, so that when we do the extractions we can control the temperature very well and help make the extractions very reproducible. So here is SPME, the solid phase micro extraction, and basically it operates like a ballpoint pen when you push the end. When you push the plunger here, the fiber, the retractable fiber, can be exposed to whatever you want to sample. And when it's exposed, then there's a coating on the outside here, and the coating is represented by the bottom phase in each of these two figures here. And depending on where you put this fiber determines what you're sampling. So you can put it directly into a water sample, in which case any particular PCBs or analytes you're interested in can stick to the surface of the fiber in adsorption mode, so sticking to the surface. Or in some cases, if you put the fiber in water or in a gas, then the PCBs or the analytes can actually partition. They can kind of equilibrate into the coating, and this is called absorption. So via these two mechanisms, adsorption and absorption, the molecules can be extracted from either an aqueous sample or a gas sample, which could be the gas above the soil sample. The mass spectrometer that we use is really quite a sophisticated instrument, and it's a little bit too complicated to describe in a few minutes. But in short, it takes quite conventional technologies that was patented back in the 70s, called an ion trap, and basically uses a very different symmetry or geometry for storing ions and mass analyzing ions. So what we're doing is we're taking PCBs. Here's a PCB with 6 chlorine atoms here, and we knock an electron off to form an ion, and then we can move that ion around in this trap and eject it at a very specific time and determine its mass. And its molecular mass here is about 360, which is what we see. But it also fragments, and these fragments actually help us determine how the molecule is put together and therefore help us identify it. We can use this this is a database spectrum, and we can collect a spectrum on our instrument, compare it to this database, and see how well we match it. So this is a way of identifying the compounds in this particular instrument. Now, a lot of the work we've done is in trying to establish the best conditions in the extraction process and in the separation process and the detection process to see how best to analyze, to get the best limits of detection for these PCBs. Here's a highlight of some of the things we've optimized. One is the extraction time. So if we extract for longer, the SPME fiber is able to pull more of these PCBs out of the soil, out of the headspace above the soil. And here's an example for 5 particular PCB congeners in an aerochlor mix. And this aerochlor mix is, I think, aerochlor 1260, a standard mix. So 30 minutes is significantly better than 10 minutes, and there were other times we looked at as well, but this is the optimum that we went with here. Here is the peak areas, or in a way that's representative of the amount that you're removing when we treat the soil differently. And if we add acid and potassium permanganate, This helps weaken the interactions between the PCBs and the soil particles and helps liberate the PCBs. And when you liberate the PCBs, they're easier to find. So if we add this acidified oxidative mixture, we release more of the PCBs and our detection limits are better. So this is kind of optimal conditions here. Clearly not perfect to take all these chemicals to the on-site to be able to make these measurements, but if we want the best detection limits, that's going to be necessary. If we don't add anything to the soil if we don't add anything to the soil, we can still see PCBs, but the detection limits are much worse. The peaks are much smaller for a given quantity in the soil. We can agitate the soil a little bit and help kind of form equilibration faster, and when we agitate, the peak areas are slightly larger, so the detection limits will be a little bit better. And down here we can see that we've tested the acidification or basification conditions, and in short, in the absence of the potassium permanganate, there's no real benefit to having acid or base. So the fully optimized procedure that we've come up with so far is basically to take between 0.1 and 0.5 grams of soil, to weigh it precisely, put it in a 20 ml glass vial, which is about this tall, and then add the acidified potassium permanganate, and then to put the cap on and put that in this aluminum kind of oven, and put the SPME fiber in the air above that soil for 30 minutes, and the PCBs will evaporate out at 100 degrees and stick to the fiber coating. We then remove the fiber and put it in the instrument, and the instrument is set at 270 degrees, and then all the PCBs come off the fiber, and then we analyze them on the gas chromatograph. For Arochlor 1260, the one that was of primary interest here on site, the detection limits we've established is about 10 parts per million, which is certainly adequate for the purposes of identifying whether or not there are PCBs there to be of concern. The recoveries, the percent recoveries in terms of how the percentage of PCBs you can actually remove from the soil when you inject a known amount, if we have no soil, just water, we can remove about 62% of the PCBs from water. And if we have real soil, the best we can remove is about 16%. But it's quite consistently 16%, so it can be quite quantitative. For dioxins, we've tested this method for dioxins, and even with some modifications to the procedure, it's much, much worse. Dioxins are much harder to get in the air above the soil, and so much harder to remove by these methods. Here's an example of what the data looks like. This is an EPA 8082A mix. It's a mixture of 19 PCBs, and they use this particular mixture because the presence and the relative abundance of certain peaks can help us identify whether we have Arochlor 1260 or Arochlor 1248 and things like this. So if we can identify all of these compounds, if we can detect them all, we can determine what type of Arochlor might be present in a soil sample. So here we're able to see 18 of the 19 different PCBs. The 19th one is off the end here, and an internal standard that we deliberately add to. At any particular time, now a lot of GCs can separate compounds like this, but if you only have an electron capture detector or some kind of non-selective detector, all you know is that something elutes at a certain time. You don't know what the compound is. On this particular portable instrument, what we have is a mass spectrometer, and we can go in at any given time and look at the fragment ions that are coming out, and there may be a molecular ion and some fragments, and we can compare these to a database and see what we may have. So we can actually use this instrument to identify the compounds we're interested in. If there were peaks that showed up at odd times that we didn't know what they were, we could use this to help identify unknowns as well. Here's an example of a 10 part per million Arochlor 1260 that was deliberately spiked to a soil sample. And this is just a kind of transparency here. We're showing the entire chromatogram, and what we can see at the beginning here are some peaks that always show up in every single run. This is kind of the background, and we know to ignore these peaks. We can kind of correct for them. And what shows up in the soil sample that's not present in every run are the PCBs that we added to the soil. So we can zoom in on this particular, any given time here, and look at a fragmentation pattern and identify a certain PCB. Here are some examples of different Arochlors mixtures. So we've demonstrated it for Arochlor 1260. Here's a 1016 because the average number of carbon atoms here is going to be 10 instead of 12. It's a much lighter mix, and so it shows up much earlier in this chromatogram. And there's a mixture of 2 chlorinated biphenyls, or 3 chlorinated, 3 chlorine atoms and a biphenyl, or 4. and very little in the way of the heavier congeners or highly chlorinated. And as you go up in terms of the Aerochlor 1232, 42, 48, 54, and 60, you can see the Aerochlor 1260 has the largest number of multiply chlorinated biphenyls, so these 7 chlorinated or 8 chlorinated. So basically we can use this to determine the difference between the aerochlors that may be present in a soil sample. Here's just a kind of a more detailed look at the percent recoveries we've established. The recoveries are, vary a little bit for specific PCB congeners in an aerochlor mixture, but again, these are the congeners that help us identify which aerochlor may be present. But there was a significant difference in terms of when you have no soil versus soil. The soil certainly holds on to the PCBs a little bit more than a glass vial would, even when you add this acidified potassium permanganate. Just an example of the semi-quantitation that we have, replicate injections here at different concentrations of aerochlor in soil. And we get different, basically the bottom line is the more PCB you have in the soil, the larger the peak area. And so you can establish a calibration curve here so that when you have an unknown and you have a certain peak area, you can read off a certain concentration of PCB in that soil. As I mentioned before, we have tested this method for dioxins, and here's an example of a dioxin mix that we inject. We are able to identify some of the lighter or smaller dioxins, and the heavier ones basically don't elute. They're just too intransigent to analyze here. So the recoveries are much worse, the detection limits are much higher, they're much worse, and so it's really not realistic to use this particular instrument or the conditions that we've tested for dioxins in soil. This instrument looks to be much better for more volatile components, for smaller molecules, for volatiles. And one example of interest on this particular site is trichloroethylene. And this is another organic solvent that's known to be contaminated in the environment there, as on other sites. And what we can see here is these 3 major peaks in this chromatogram are the ones that we know to be present in every run, as they're quite consistent, and we can subtract those or ignore them. There's an internal standard that we deliberately add here, this trichlorobenzene. And then we have the trichloroethylene over here, which looks very small when it's scaled here, but if we zoom in, we can see it more easily. And again, we can go in at this particular time and identify it. Here's a calibration curve for the quantitation of TCE in solution here. In this particular case, we're interested in TCE in groundwater instead of in the soil. And so here's an example of a calibration curve for TCE in water. So again, if we took an unknown and analyzed it, we could read off the peak area and determine the concentration. But the bottom line is we can take about 5 milliliters of groundwater that may or may not be contaminated with TCE, put it in a 10 milliliter glass vial with a stir bar and stir it up, and then do this headspace SPME sampling, so put the fiber above the water at room temperature or whatever the ambient temperature might be outside, and the TCE will evaporate out the water and stick to the fiber. We can then take the fiber out of the headspace and put it in the instrument and analyze for TCE. So in short, just to summarize the developments we've done in the past couple of years here, we can detect down to about 10 parts per million, at least Aerochlor 1260 in the field. So we've done an on-site demonstration of this instrument in less than 45 minutes, and that's from starting with the raw soil sample to the final result. We know we can identify other PCB aerochlors, but we have not yet tested the limits of detection for the other aerochlor mixtures. We need to investigate, if this was going to be used, we'd need to investigate the use of internal standards a little bit more. We didn't use internal standards for a lot of the work we were doing, but in terms of getting better precision for the quantitation, that's going to be necessary for future work. If we want to do a better job of more accurately assessing the PCB concentration or the aerochlor concentration in the soil, we need to know the water content of the soil, because these concentrations are usually listed as the mass of PCB per dry mass of soil. So if the soil contains 20% by mass of water, we need to know that so we can account for that water content. And we don't yet have a way of determining the water content of soil in the field. The best extraction efficiencies were in oxidative acidic conditions, and this is not ideal, but it's certainly possible, it's doable in the field. The method is not yet applicable to mixtures of aerochlors. That's going to require some complicated chemometrics or statistics to be able to pull apart these complicated mixtures. Or for weathered aerochlors, and weathering is when the aerochlors may be exposed to UV light or temperatures, and they may biological degradation, microbial degradation, and we haven't yet assessed the ability to identify aerochloros after such processes. The method is not really suitable for dioxins, but it is very suitable for TCE, this trichloroethylene in aqueous solutions or groundwater. And now with the detection limits are much better, down to about 20 parts per billion instead of 10 parts per million for the PCBs. We haven't yet tried very sophisticated statistical methods, but we could use some chemometrics to help identify these aerochloros or mixtures. And the bottom line is that this particular instrument is not as reliable as benchtop instruments. There were occasions where it would get plugged or blocked or things like that. But certainly is able to make the kinds of measurements in the field that could help with on-site remediation in the future.